Hey guys, so today we're doing an AS mechanics paper, Mechanics 2. And the first question is one of our classic horizontal plane questions. It's not too hard. So what we have is a flat plane, horizontal plane, with some particle, which I'm going to, describe by a box because it's just easier to draw. And then you've got this force acting, like so, at 15 degrees above the horizontal. So what that means is if you draw a horizontal line, then you rotate anti-clockwise 15 degrees. That's, if you were going down sort of this way, like so, that would also be at 15 degrees to the horizontal, but it would be written as minus 15 degrees because it's going the other way. So this is just convention, so you know that the force is acting upwards. So what other forces do we have acting? Well, we have the mass of the box, of course, like so. And we also have the reaction force. So that's mg, that's r. This force will have a vertical component of 10 cosine of 15. And it'll have a horizontal component, 10 sine of 15. And there'll also, because the thing is moving, there'll also be this frictional force acting like so, force of friction. So our first, you got to remember that the big equation for these is that the force of friction is equal to mu times r. And r is basically whatever it takes to balance the forces in the vertical direction so that the thing doesn't go into the ground or rise up off. Because remember that if you've got an unbalanced forces, the thing is going to move in that direction. So because the thing isn't moving vertically, only horizontally, the vertical forces must be balanced. So if we add them up, we see that r must be equal to mg minus 10 cosine 15. So what's happening here is that because this force is being applied, the object effectively weighs less according to the reaction force. So the ground has to do less upwards force on the object to keep it from sinking. This is going to be, so that's actually, God, this is actually, it belongs to the next question. Oops, that goes down there. Getting ahead of myself here. What I meant to say was that we're given this information about its motion. We're told that after 10 seconds, the speed of the particle is 3.5 meters per second. So initially it's at rest and it's accelerated to 3.5 meters per second, which means the acceleration must be 0.35 meters per second squared, because that's delta v, change in velocity over change in time. So in the horizontal direction, our forces are 10, so this is fx, the net force in the x direction is 10 sine of 15 degrees. Oh God, and then another mistake, this is sine and that's cosine, sorry about that. I'm sure you've noticed that that was a mistake. So this is sine, so this is 10 cosine of 15 degrees minus the force of friction. And this must be equal, because it's the net force, to the mass times the acceleration. So we know what 10 cosine 15 degrees is in our calculator. We know what the mass is. We know what the acceleration is. And so this gives us the force of friction. No problem. So now we use the force of friction is equal to mu times r. And this fact that r is mg minus 10 sine of 15. And as you can see, we know what the force of friction is. We know what r is because we know what mg is, and we know what 10 sine 15 degrees is, and therefore we can solve for mu. Okay, question 2. So this is a particle moving in a straight line and not under a sort of variable acceleration. So you know that if you have a constant acceleration, then the position is just equal to initial position plus initial velocity times time plus 1/2 acceleration times time squared. And this is only for constant acceleration. This thing doesn't look anything like that. It's got this weird, it's got okay, it's got a t squared term there, but it's also got this extra bit that depends on t to the 3/2. So that means the acceleration is not constant. So they want us to find the time at which the acceleration of the particle is 0. Well, we just use differentiation, right? We know that v, the velocity of the particle, is ds dt, which in this case, we're just going to do some differentiation, is 4t minus 3/2 times 80 t to the 1/2. And this thing is equal, 80 over 3. So this thing is equal to 40. And then acceleration, which is dv dt, you just differentiate a second time, and you get 4 minus 40 over 2, 1 over t to the 1/2, or t to the minus 1/2. Now we're saying that this is equal to 0, and you can see that you rearrange. You will get that square root of t is going to be equal to 5, so t is 25 seconds. Okay, nothing too hard there. They require you to know these two facts and then be able to differentiate a polynomial. The only slightly tricky bit being is what you do with a fractional exponent. But remember, it's exactly the same rules as with an integer exponent. You just subtract 1. So it's 1/2 minus 1 is minus 1/2, which is 1 over. So this is equal to t to the minus 1/2. Your rules of exponents, no problem. And then solving it in that way. Okay, now they want us to find the displacement and the velocity of the particle at this instant. Well, I think that's pretty straightforward. We know that t is equal to 25 seconds. Therefore, we know that the velocity is going to be equal to 4 times 25 minus 40, 25 times 25 to the 1/2, because that is the equation for velocity that we got. And the position, we do the same thing. We just plug it in. 2 times 25 squared minus 80 over 3 times 25 to the 3/2. And that just goes in your calculator and will give you the solution you need. So what you'll find is that the velocity, that they are both less than 0, which means that when the acceleration is 0, the thing is moving in the sort of negative direction to what we initially expected and defined. And it has also moved a negative displacement. So it started over here, maybe it went there for a while, but then it ended up all the way over there. And that's what the negative sign means. So don't be freaked out if you get a negative answer. Okay, question 3. So we have a boat being pulled along by 2 people with ropes. And they're at different angular separations from the horizontal. So they're asking you to find the total force exerted by the 2 people in the direction of the river. So in the direction, that means resolve along x-axis. Well, that means fx, basically our net force in the x direction. Well, that is this guy, which is 60 cosine 25, and the other guy, which is 50 cosine 15. So this is just the sum of these, 60 cosine of 25 degrees plus 50 cosine of 15 degrees. So that's pretty straightforward, and you get something like 103 newtons. Now they want the magnitude and direction of the resultant force exerted by the 2 people. So we know already that Fx is 103 newtons. And now we can work out Fy. Well, that's just the sort of sine versions. That's just the vertical versions. So that's going to be 60 sine of 25 minus, and remember it's minus because they're acting in opposite directions, right? Minus 50 cosine of 15 degrees. And then to get the magnitude and direction, that's the same thing as going from Cartesian, y and x, to, instead of being x units along and y units up, it's this many theta angles rotated and r distance out. So you see that if you ever want to remember the formulas for going between polar and Cartesian, you just draw this triangle and realize that r here is just the hypotenuse of this triangle, which has x as a base, x units as a base, and y units, because it's a right angle triangle, right? And y units as a height. So if instead I'm in polar coordinates, my force, the magnitude of my force, also written like this, is the square root of fx squared plus fy squared. And my angle, well, you recognize that the tan of y, the tangent of theta is opposite, which is y, over adjacent, which is x. So theta is going to be equal to inverse tangent of y over x, or fy over fx. And yeah, that'll, if you just plug that into your calculator, you'll get the correct solution. Okay, question 4. So we've got a girl on a sledge at the top of a slope. So let's draw our slope. She starts out over here, and the slope has a length of 100 meters, and it's at angle 20 degrees. So that means that this height must be 100 times the sine of 20 degrees. And they want us to, she starts at the top at rest, sorry, not at rest, with a speed of 5 meters per second. And she ends up at the bottom with a speed of question mark, which we want to find. Let's call it v. And they were told that there's no resistance to the sledge's motion. So that means no friction, which means no work is done by the sledge on the slope. You know, we're not dissipating any energy through friction. We're just converting freely between potential and kinetic energy. So obviously this is a conservation of energy problem. So at the top of the hill, what is her energy? Well, she's got some kinetic energy, 1/2 mv naught squared, and she's got some potential energy, mgh. And this is going to be equal to, by conservation of energy, the energy that she has at the bottom, which is just all kinetic. So it's 1/2 m v1 squared. So we have 1/2 times the mass, and you'll notice that the mass cancels out. So we don't actually need to know her mass. You just divide everything by mass. So you get 1/2 times 5 squared plus g, which is 10, times the height, which is 100 sine of 20, is going to be equal to 1/2 v1 squared. So we're looking for v1 squared. We can easily do this by with our calculators and get the correct answer. So now instead they're saying, let's say that she does experience friction, resistance to motion, and they've told us the amount of work that gets done. Well, this is exactly the same situation, except you've got an extra term. So you have kinetic energy plus potential energy at the top is now going to be equal to kinetic energy at the bottom plus the work done, which makes sense, right? She's got all this energy available to her at the top of the hill, and some of it gets used up doing work by fighting friction, and the rest is available to do for the kinetic energy. So this would be 1/2 mv v0 squared plus mgh is equal to 1/2 mv1 squared plus 8,500 joules. And again, we know everything except the mass. So we're given v1 at this point. So all we need to do, the only thing that's unknown is the mass. We know h, we know g, we know v0, we know V1, we know the work done, and we can find M. Okay, question 5. So this is another ramp. They love ramps. A particle of mass m is resting on a rough plane inclined at 30 degrees to the horizontal. So let's draw our rough plane. I may emphasize to you, always draw a diagram. So we have a particle, which I'm going to make look like a box, resting on the plane. And we've got to draw the forces that are acting on it. So we have our mass, which has, we can resolve into 2 components with a right angle between them. And this angle, so this angle is 30, and that angle is also 30. That's just, you should be used to seeing that, but automatically know that if the wedge has an angle of 30 degrees at the at the narrow end, or the end at the bottom, then that same angle over here in this point when you're resolving the mass. This should be second nature by now. And then we're also told there is a force of 10 newtons applied to the particle up the line of greatest slope of the plane. Now that just means, you may have seen this before, but don't be confused. The line of greatest slope just means it's acting like so. So it means it's not coming out of the screen. It's not going, it's not sort of making its way up the slope in a slanty sort of way. It's just going straight up as fast as it can, which means we can just treat this as a 2-dimensional problem. And it says that it is just sufficient to stop the particle sliding down the plane. So at first this is 10 newtons, and then later on it's 75 newtons. And at that point it is just about to slide up the plane. So this question is asking you about friction. So in scenario, so you know what, I will try and make a copy of this so we can look at the 2 different scenarios. There we go. So scenario 1, this force is 10 newtons. Actually, I want purple for the friction. So this force is 10 newtons, and the thing really wants to move down the plane. So that means that the force of friction is acting against where it wants to move. So it's acting like so. So it's kind of teaming up with this 10 Newton force to stop the thing sliding down the plane. On the other hand, say the force pulling up is 75 newtons. Suddenly, the thing actually wants to move up the plane. So what it's saying is that the force of friction now is going to be acting down to fight where the motion wants to happen. So force of friction is always opposite to motion. Even if the thing isn't actually moving, it means opposite to the way it would move if the friction wasn't there, if you know what I'm saying. So oftentimes with these problems, you have to think about what would happen if friction wasn't there in order to work out the direction that friction would be acting. So scenario 1, let's resolve our forces. So they want the coefficient of friction and the mass. So in situation 1, we have the force of friction acting up the slope. So we have, if we balance the forces, we get that 10 minus mg sine of 30 degrees. So that's those 2 forces plus the force of friction is equal to 0. And here, in this scenario, we have 75 minus mg sine of 30 minus force of friction is equal to 0. And in both cases, the force of friction is equal to mu times r, and r is just acting out like that in order to balance the vertical, or the into the plane action of the weight. So it's mu mg cosine of theta. And that's what those 2 are equal. And now we see we have two equations for two unknowns, which is fine. We have equation 1 and equation 2. So remember that we always, if we have a certain number of unknowns, we need exactly that number of equations to solve for them. So to see how we do this, we first take equation 1 and add it to equation 2. So we add left side to left side and right side to right side. And that gives you 85. These mass terms, these ones of the mass pulling down, cancel out. 85 minus 2 mu mg. Wait, whoops, sorry. That's not the one that cancels out. What I mean to say is that the forces of friction cancel out because you're adding them together. So it's plus force of friction minus force of friction. And you get two copies of this guy. So it's 2 mg sine of 30 degrees is equal to 0. And you can solve this in your calculator and get that the mass is, I think, 17/2. Now we take question 1. And in fact, we can just now plug in our value of mass into equation 1. So we get that 10 minus mg sine of 30 plus mu mg cosine of 30. We know m now, we know g, we know these are just numbers, so we can solve for mu. So the key thing here was to understand that the force of friction stops the thing moving in either direction. It stops it moving wherever it wants to move up until a certain amount. Obviously, once the force that's pulling it up or it gets too big or too small, the thing will start to move anyway. But at these 2 points, the force of friction is enough to combat it. And so you can construct two equations and solve it for the two unknowns. Question 6. Okay, so this is one about power. And the equation for power, I'm going to write as, so power is delta E, change in energy over change in time. So the amount of energy that's poured into the system per unit time. Well, that's going to be equal to work done over change in time. So you see that it's a constant resistance to motion, and it's at a constant speed. So all of its energy is going into fighting friction and maintaining the constant speed of the car. So just disentangle in your mind the idea of energy input or net force and velocity. It's force and acceleration. So as long as you're not accelerating, the forces are balanced. And the only reason, if you had a perfectly smooth plane, you could move on it forever at a constant velocity without any energy being put into the system. But because we've got friction, we need to put energy into the system to exactly cancel that if we want to move at a constant velocity. That's why in our everyday experience, we associate putting in energy with moving. And if we stop putting in energy, we'll slow down, but it's only because friction is there. Anyway, you know this. So work done, well, what is work done? That's just force, the resistance force times the distance that the thing has traveled. And what is the distance traveled divided by the time taken? Well, that's just the velocity. And if you plug that in, you get 400. So that's for the whole system. So there's 400 newtons of force acting on the whole system, 300 for the van and 100 for the trailer, times the velocity, which is 25. And this will give you 10 to the 4th joules per second, which is 10 to the 4 watts. So a watt is a joule per second, energy per second, as you can see here, energy per unit time. Okay, now they want you to find the tension in the cable. So let's think about the trailer, for example. Now it's got some force of friction acting on it, and it's being pulled forward by the tension. Well, what's the force of friction? It's 100 newtons, and it's not accelerating in or out, so therefore the tension must be equal to 100 newtons. Now they are doing a slightly more complicated scenario, and the van starts going up a hill and its power increases. So here's our hill, and here's the van, and here's the trailer, and there's the connection between them. And they've got this new driving force. So and the new driving force, again, remember the driving force is the power divided by the velocity. So at this point, when the at the instant the speed of the van is 20 meters per second, the power is always the same. This is going to be equal to 1250 newtons. So we've got 1250 newtons being poured in. Now what's happening at the trailer? Well, the net force on the trailer, that's going to be equal to the tension pulling it up minus mass of the trailer times g times the sine of 4 degrees, because remember the masses are acting like so. So we're looking at forces going in this direction. So it's going to be sine of 4 degrees. Mass of the trailer, g, sine of 4 degrees, minus the friction force, because the friction force is always acting against the motion, so it's acting like so. And that's 100 newtons for the car. And for the trailer. And this is equal to the mass of the trailer times the acceleration, because it's the net force, F equals ma. Now the net force for the car, well, what's pulling it upwards? That's going to be the driving force. Sorry, this is the F driving. The driving force minus mass of the car times g times the sine of 4 degrees minus the friction force, 300, minus the tension, because it's being dragged by this, the trailer's dragging out via the tension. And this is equal to 3000 times the acceleration, where this is mass of the car. So and that was 500. So you see the accelerations are the same. They have to be the same because the thing is sort of moving as a unit. It's not like one of them, like the car is speeding ahead and leaving the trailer behind. It'll pull the trailer on at exactly the same acceleration. So we can then solve for A. We can, so if we have this as equation 1, equation 2, we have two unknowns. We have A and we have T. So if we take, equation 1 plus equation 2, this will give us acceleration. And then we can plug in to get the tension. So exactly the same as before. Okay, question 7. Final question. A car starts from rest and moves in a straight line from point A with a constant acceleration for 10 seconds. Then it travels at constant speed for 30 seconds before decelerating uniformly. So the velocity time graph is going to look something like this, where that's 10 and that's 40 seconds. So at this period it's accelerating, at this period it's a constant speed, at this period it's decelerating. Remembering that the acceleration is the slope of a velocity time graph. So let's think, what is the total distance traveled in the first 40 seconds of motion? Well, we know that what we need is the velocity at some later time at this this constant. So it only cares about the sort of, this question only cares about this and this. So let's call that point A. Let's call this 1. That's 2, and that's B. So when you're going from A to 1, the distance traveled is going to be 1/2. Okay, so I'm going to call this region 0. That's going to be region 1. That's going to be region 2. And so this is going to be distance traveled, 0, is 1/2 times the acceleration during region 0 times the time spent in region 0 squared. And we know what that's going to be. That's going to be 1/2 times 3 times 10 squared, which is 150 meters. Now, we also want to know what is the velocity in region 1. Well, velocity 1 is going to be equal to initial velocity, which is 0, plus a0 times time 0. So it's been accelerating all this time, so the velocity at the end, which is the whole velocity, and then sort of stays constant during the second time. So that's going to be equal to 30 meters per second. And therefore, the distance traveled during region 1 is v1 times t1, and that's going to be equal to 900 meters. So the total distance traveled is the addition of these two, 1,050 meters. So the big thing is actually really finding this velocity. And once you do that, you can also picture it as distance traveled is equal to the area under a VT graph. So you could have just, found the 30, marked it there, and then sort of this as a triangle. So it'd be 1/2 times 10 times 30. And then this one would have been, oops, there we go. And then this thing would have been the V1 times t. So if we go here, so now they're making it a little more complicated, and they're talking about the motorcycle starting at some later stage after 20 seconds and accelerating uniformly to some speed and then decelerating, and basically it hits B at the same time as the car. So its velocity time graph, it's going to start at some 20 seconds. It accelerates, it goes along, and it comes back down at the same time. And it spends 30 seconds here. So that means this, if this starts at 20 seconds, we don't know how long it takes to get there. So this period is 30 seconds. And then it decelerates, and it reaches point B at the same time that the car reaches it. So first, the car. Let's think about the car, because now we have to think about the car going all the way to B. Oops, that's a crazy line. The car. Well, going from, so in zone 3, in the third, actually zone 2, so I went from 0, 1, and 2, so it's the third zone, it's number 2. Sorry for the confusion. We're told that the total, so it's a distance traveled, S2, that's going to be equal to the total distance, which we're told here is 1.5 kilometers in the question, 1,500 meters, minus whatever was traveled before that we found, 1050, so that's equal to 450 meters. And the velocity, oops, God, I don't know what's wrong with this pen. Velocity in region 2 starts at 30 meters per second. So V final right at the end is 0, because it ends up at rest at the end. So that's equal to the initial velocity minus the acceleration in region 2 times the time spent in region 2. And that means that since this is equal to 0, that means that A2 T2 is equal to 30. We also have that the distance traveled, which is 450 during this time, is equal to initial velocity times t time spent minus 1/2 times a2 times time 2 squared. And if we pull both of these together, we get that time spent in the second zone by the car is 30 seconds. So therefore, after all of this, we get that B is reached after 70 seconds. Because if we go back up, we see that there was 10 seconds spent in zone 0, 30 seconds spent in zone 1, and then another 30 seconds spent in zone 2. So 40 plus 30 is 70. Okay, so now for the motorcycle, well, they really haven't given me much space here, so I'm going to make this really small. This was all about finding the amount of time that it took for all this to happen. So for the bike, I'm going to draw a diagram here, more detailed one. So if this is our velocity time graph, we have it starting at 20 seconds. It comes up with, it accelerates. Remember, this is velocity time, so the slope of this graph is acceleration. And we're saying that its magnitude of acceleration is a. Then it spends some time at a constant acceleration, and then it decelerates at much slower rate. So what they're saying, this is, a2, which is equal to 1/3 a. And we know that it reaches here at 70 seconds. And because it spends 30 seconds here, we can figure out, let's call this time, I'll do it in a different color just so we're not going to lose track. I'm going to call this period of time delta t1, and this period of time delta t2. So I'm going to divide this into region 1, region 2, and region 3. And actually, I'm going to change that to be A3. Okay, we're almost there. So at this point, at this constant velocity area, that's big V. That's what they've called this velocity. So this big V is going to be equal to A1 T1, or AT1. And that's going to be equal to 3 times A3 times T1. So I'm going to work with this A3, and then I'm going to go back to A because they asked me for A, but it's easier this way. And we also know that the final velocity here is 0, and that's going to be equal to the initial velocity at the start of section 3, which was big V, minus A3 times T3. So these two things are true. And A3, T3. And if we compare them, we will get that wait, this is 3, which is then that's going to be 1/3 A. So we leave this in terms of A3. And if we compare these two, we will get that, we plug in our value for V into there. We get that delta T2. Let me call it delta T3 because this whole region is called 3. So we have delta T3 is equal to 3 times delta T1. So that means that the amount of time, the total amount of time that this thing has spent, this motorcycle has spent traveling, is 50 seconds. It starts at 20 seconds, ends at 70 seconds. So we have that 50 seconds is equal to the 30 seconds it spends in the middle plus delta T1 plus delta T3. And delta T3 we've just shown is 3 times delta T1. So this is equal to 30 plus 4 times delta T1. And we can solve that and get that delta T1. Delta T1 is equal to 5 seconds. And therefore that delta T3 is equal to 3 times that, which is 15 seconds. Okay, we're still low on space, huh? So I'm going to get rid of that. And what am I going to do? I'm going to drag this guy over here. That guy there. That guy can go. Where even to arrange all this? Okay, this diagram is very important, so I'm going to keep it full size. I'll put it there. This guy can now be minimized. Okay, great. So we've got delta T1, 5 seconds, and delta T3, that's 15 seconds. Now, this also gives us that big V, which is A times delta T1, which is equal to 3 A3 delta T1. So that's going to be equal to 15 A3. Okay, almost there. So we know that the total distance traveled, well, that's equal to the same, it still traveled the same distance before, so that's 1,500 meters. So that's going to be equal to, initial distance traveled, which is nothing, plus the distance traveled during period 1. So that's going to be 1/2 A delta T1 squared, plus the distance traveled in distance 2. And that's going to be equal to V delta T2, sorry, not delta T2, V times 30. And it's a constant, so there's no acceleration, so that's fine. Plus the distance traveled during section 3, which is V times 30 again, but now minus 1/2 A3 delta T3 squared. Whew. So that's quite long and involved, but we're solving for A, right? We know delta T1, that's 5 seconds. We know V, big V, in terms of A3, so that's 15 A3, which is 5A. We know what 30 is, it's a number. Here's V again. Here's A3, which remember is 1/3 A. Delta T3 we know is 15 seconds. And all of this, if you plug it in, give you a very final answer of A being 7.5 meters per second squared. So yeah, that was quite a mission, which is probably why it's 6 marks. So you had to first address the car in order to get the time where everything ended. Then you looked at the motorcycle and used the 2 facts that you know about this velocity V, this big V that it spent all this time in. Then you have to use plug in all of that information into this long equation for the distance traveled and use the fact that you know what the distance traveled is. So yeah, it's quite, basically with these things, the best strategy is just to work on all the things that you can with the information you're given, and you will probably need to use all of those things. So they want the displacement time graph for the motion of the car. So this is a little different from the velocity time graph. So let's think. The car, if we look back over here, what did we find? Well, we found that it was accelerating at a certain time. So the velocity was increasing. Then the velocity was constant. Then the velocity was decreasing. Okay. So what we really, yeah, the velocity was decreasing at a more gentle rate. So what is the velocity in terms of displacement? Well, velocity is just ds dt, right? Which means velocity is the gradient of a displacement. You know what that means? Time graph. So in between t equals 0 and t equals 10 seconds, the velocity was increasing. So here, v was increasing. Then between 10 seconds and 40 seconds, maybe out there, velocity was constant. And now between 40 seconds and 70 seconds, velocity was decreasing. And because the velocity is the slope, that means that we started over here with a 0 slope, because velocity was 0 at the beginning. Then the slope started increasing. So it's not just that the thing, you know, a straight line has a constant slope. So we're not looking for a straight line. We're looking for something where it starts off shallow and then it starts getting steeper. I.e., we're looking for a curve like this. So the curve goes like so. Then the velocity is constant. Well, that just means, okay, I think I've kind of gone over enthusiastic with this curve because I'm not going to be able to fit it on. But it's you know, it's a curve. Then the velocity is constant. So that means the curve is just a straight line. Then the curve starts decreasing. So if I'm starting a curve like this and I want the curve to start decreasing, it's going to get shallower and shallower and come like that. So from here, it starts petering off. So this is the shape of your thing. And at this point, the velocity was the displacement. Displacement was 150 meters after 10 seconds, and over here it was 900. And at that high point that I couldn't fit on the graph, it was 1500. Sorry, not 900. 1050. So yeah, that's the time graph. The thing they want from you is that you get the curve right. So they want you to know that the velocity is the gradient of a displacement time graph, and know that increasing velocity means the gradient of the curve itself is increasing. It's getting steeper. And yeah, I think that's all that you need for that question. I hope that was all clear to everybody. Let me know any questions you have in the forums, and I'll see you next time. Bye.